the surface being a rubber sheet and just to a bigger surface, it could be all lumpy and junk, wouldn't matter. As long as the divergence is 0 between the original surface and the blowed up surface, the flux is the same. This math is why field line pictures make sense. Field lines start where the divergence is infinite, or where the divergence is non-zero. All right? So if the divergence is everywhere 0, the only place where field lines are starting is where the vector field is undefined. Those are where the charge are for physics, and that's why the picture makes sense, because so that, I mean, that's essentially the idea of the divergence. Why it's called divergence is this. But any questions? Yeah.
What would the divergence represent physically, if it were represented?
Well, it represents how the vector field is flowing out locally, essentially. It's how the vector field is flowing out. But it's more than just that, see, because it has to be, if the divergence is non-zero, that means it's not only is the vector field flowing out from the point, it's flowing out from the point in sort of some kind of increasing fashion. You know, like this, this is called the Coulomb field. This field, unless I enclose the origin, right? Yeah, I mean, it's expanding everywhere outward. But if I was to take any particular region, whatever goes into one side goes out another side. If the divergence is non-zero, there's going to be more field lines going out one side than another side, something like that. But I don't know if I may not have really answered your question, but that's a good question to think about. Oh, so what about Stokes theorem? What about Stokes theorem with a hole? Let's talk about that a little bit. Although I guess I should do a follow-up example for this one while we're at it. Let me do my example 6 here. What if you had f was equal to, I don't know, like x, y, z over, x squared plus y squared plus z squared to the 3/2. So that's the one we just did, right? And then plus, like the vector x minus 1, y minus 2, z minus 3 divided by x squared plus y squared plus z squared. Oh, my bad. X minus 1 squared plus y minus 2 squared plus z minus 3 squared to the 3/2 power. So what's the problem with this one? Let me just get straight to the point here. Undefined where? 0, 0, 0, and what? 1, 2, 3, right? But if you think about it, by the symmetry of the formula, and just by the chain rule, if you will, with respect to partial differentiation, it should be fairly obvious to you that if the divergence of f is equal to 0, like the divergence of the f from example 5 is equal to 0, then the divergence of this vector field is also 0. So we have the divergence of f is equal to 0 everywhere except where? So if you can imagine this, we've got to watch out. We've got the origin, and we got some point out here, let's say 1, 2, 3. If I calculate the integral of this vector field, the flux of it through a surface, I have to ask myself the question whether or not one of these points is included in the surface. all right? So a couple of different cases, you know, if I've just got some closed surface out here, right? You know, not containing, not enclosing 0, 0, 0, or 1, 2, 3, then what would be the flux through that? Well, it's just the triple integral over the region which it bounds, and the divergence of f is what? It's 0, so it's equal to 0. The flux through that is 0. Again, assuming that that is a closed surface which doesn't include the origin or 1, 2, 3. Does that make sense? But let me point something else out. If we were to, say, put a little bitty sphere right here, right? Or if we were to put a little bitty sphere right here, right? Let me say that this is the sphere of radius, let's call it epsilon, centered at 1, 2, 3. Or down here is the sphere of radius epsilon centered at 0, 0, 0. What's the flux? You know, what's the flux through those? Can you guys tell me? Now you said 4 pi each. What about the other part of it? Yeah, let me make myself some room here to jibber jabber. Right, so like for example the 1, 2, 3 one, we have what, I need to come up with some names for these things. Let's call this F0, let's call this guy F1. So we've got F1, rather F0 plus F1 dot ds, right? But the surface integral is linear, so we can break that up. We can say, well, that's the integral of F0 dot ds plus the integral of F1 dot ds. Now, the only way we can do this is if the resulting integrals are finite, and, well, we know because we've calculated. All right, so here I've got the sphere of radius epsilon 1, 2, 3. And I'm just saying that epsilon is small enough so that it doesn't end up encircling the other pole, the other place where it's not defined. So look, in all of epsilon 1, 2, 3, we have the divergence of F0 is equal to 0. Throughout the whole thing, even the center, right? It doesn't have any problem with the center 1, 2, 3. So this, for the F0, I can legitimately apply, you know, the divergence of F0 dV over the, you know, the ball of radius epsilon centered at 1, 2, 3. And through a completely legitimate application of the divergence theorem, that piece is 0. But on the other hand, this right here, by the calculation that I've already done today, by the fact that it's the same formulas, I just shifted them to 1, 2, 3, right? So you could go through the same song and dance, but essentially by the calculus in example 5, we already know that's going to work out to 4 pi. So this would work out to 4 pi, and so that's why we get 4 pi. And by essentially the same argument, the integral around the little sphere that encloses the origin is also equal to 4 pi. All right? What I'm showing you right now is the mathematical justification of Gauss's law, essentially, for two charges. So what if you have a surface which includes both the origin and 1, 2, 3? What happens then? If I have a different color. My picture is about to get really busy, so my apologies. And hideous, too. So imagine this is your surface. Whee! Right? It includes everything. So we'll call this the UNC surface. So the flux through the UNC surface is what? It's equal to the 8 pi, but it's the logic for that is it's the flux through the epsilon 0, 0, 0 plus the flux through the 1, 2, 3 sphere. See, because the vector field, it's not defined on the entire of the interior region that's bounded by the UNC surface, but if I just punch out these little holes, pa-chunk, pa-chunk, then the vector field has is well-defined everywhere except where it's got division by 0, and we already know that the integral around these guys is 4 pi each. So by the deformation theorem, the integral around the UNC surface is 4 pi plus 4 pi is 8 pi. Indeed. All right, so what I'm showing you guys right now is more or less the highest level of understanding that I know of for like divergence theorem. And there's similar things we can do for Stokes theorem in terms of like deformation. But the first thing you need to understand is like the statement of the theorem and how to apply it for specific examples. I've done some of that in here, but of course we could do more, right? So anyway, I guess that's a pretty good place for us to stop for today. So thanks, everybody.